In this video, I'm going to teach you about Schottky diodes. They're very similar to regular silicon diodes, but with some important differences. For starters, they have a different circuit symbol. Notice how similar they look to other diodes. Make sure you don't get them confused, because they behave very differently. Okay, before I talk about what's special about Schottky diodes, I want to remind you of some basic diode concepts. In my previous video about diodes, we talked about how they only let current flow in one direction, and when current is flowing through the diode, there's a voltage drop across the diode called a forward voltage drop, or VF. Since you have a drop in voltage across a device and there's current flowing through it, you end up with some heat being generated in the diode. And here's the equation for that. VF multiplied by the current gives the power in watts. One of the main Schottky diode advantages is that they have a lower VF than silicon diodes. This results in less heat being generated. Let me show you an example. Here I have a regular 1N4007 silicon diode with 500 milliamps flowing through it. If I measure the voltage drop across the diode, it's 0.832 volts. 0.5 amps multiplied by 0.832 volts gives 416 milliwatts of heat. And that's causing the diode to have a temperature of 54 degrees. Now let's try the same experiment with a 1N5817 Schottky diode. We've got the same 500 milliamps flowing through it, but the forward voltage drop is only 0.345 volts instead of 0.832 volts. 0.5 amps multiplied by 0.345 volts gives 173 milliwatts of heat instead of the 416 milliwatts we were getting with a silicon diode. This results in a lower temperature of 38 degrees instead of 54 degrees. So basically, Schottky diodes are a more efficient way to block the reverse flow of current. You can always find out the VF of a Schottky diode from the datasheet. Make sure you check out the graph of VF versus current, because the forward voltage is going to change depending on the current. The temperature affects it too. Okay, are there any other advantages of Schottkys? Well, they tend to have very fast switching speeds, so you can use them at higher frequencies. I have a demo set up here where I'm generating a 60 Hz sine wave, and I'm feeding it into two different types of diodes, a 1N4007 silicon diode and a 1N5817 Schottky diode. These diodes are very common, and I'm just using a couple of resistors for loads. Okay, let me explain what you're seeing here. In yellow, we have the input sine wave. It's not a perfect sine wave because I'm putting an unusual load on my waveform generator with the multiple diodes and resistors. In green, the silicon diode is blocking off the negative half of the sine wave. We're successfully doing half-wave rectification, which gives us these positive voltage bumps. In blue, the Schottky diode is also doing a great job, and as you'd expect, there's less of a voltage drop. All of this is happening at 60 Hz, which is a frequency that both diodes are designed to be used with. So what happens if we increase the frequency of the input sine wave to 300 kHz? That's a frequency you'd expect to see in a switch mode power supply. Whoa, what's the matter? It's like the Schottky diode is on steroids and the silicon diode's been pushing too many pencils. The Schottky diode has no trouble with the higher frequency and successfully prevents the reverse flow of current. But the silicon diode is doing a terrible job of rectification. In every cycle, it's spending a lot of time allowing current to flow backwards before finally blocking it off. Every diode takes a certain amount of time to switch from allowing forward current to blocking reverse current. Schottky diodes tend to be very quick, so that's why they're often used in medium to high frequency applications. If you want to learn more about this behavior and how to accurately measure the recovery time of a diode, enable annotations and check out Alan's excellent video on the subject. Okay, so if Schottky diodes are quick and efficient, why doesn't everyone use them all the time? Why would you ever use a silicon diode? To answer that, I have to talk about another property of diodes called the reverse leakage current. You know how diodes block the reverse flow of direct current? Well, that's not 100% true. There's a small leak. Check this out. I have a power supply set to 19 volts, and that's connected to a silicon diode that's backwards. It's in series with my multimeter, so I'm measuring the amount of current that's flowing backwards through the diode. As you can see, the reverse leakage current is almost unmeasurably small. That's what you want to see for a perfect diode. Now let's try the same experiment with a Schottky diode. You can see that with minus 19 volts across it, there's almost 20 microamps of reverse current flow. That's a lot more than the silicon diode. Now, you might be thinking that 20 microamps is not a big deal, And if you're using a diode for reverse voltage protection, it's not a big deal. But if you're using a diode as part of something like a peak detector circuit, that 20 microamps could be significant. And across the whole temperature range of the diode, the leakage current can reach well into the milliamps, so you can't just blindly use Schottkys everywhere. Now there's one last thing I want you to know about diodes, and not many people realize this. The forward voltage drop tends to correlate with a maximum voltage rating on the diode. When searching for diodes, you might be tempted to go out and buy the diode with the highest voltage rating possible, because then you'd have a larger safety margin. Well, you can do that, but you'd be sacrificing efficiency. Try figure out what your peak reverse voltage is, and pick a diode that's rated for about 10 volts more than that. But make sure you figure it out accurately, otherwise... Thank you for watching, and make sure you check out my other videos about electronics.